Okay, I think that's it is time to start this course, and I'm really happy to announce that during this year, all courses which will be given in the frame of lectorium on algebra and graph theory, they will be given in cooperation with 3 mathematical centers. One is from Russia. This is Mathematical Center in Akademgorodok, and 2 centers in China. The first one actually is Russian Mathematics Center in Beijing, and the second one is the 3 Georges Mathematical Research Center at China, the Georges University in it. So it is my great pleasure to ask Alexander Medlik to introduce our lecturer, Roman Nedela. So Alexander, the floor is yours.
Okay, thank you very much, Yelena. It's my real pleasure to introduce my old friend and colleagues, Doctor of Natural Science, Professor Roman Nedela, who is really from Slovakia, and now he's working in Czechia. Roman is well recognizable expert in theory of graphs. His field of interest is quite rich. He is doing enumeration theory. He is author of many well recognizable work related with descent defun. Also, he is a good expert in many other fields of low-dimensional topology and geometry. Also, I should say that Roman is an excellent organizer of many international conferences and other activities. Because of his effort, Banska Bystrica, very beautiful small city in Slovenia, became well recognizable mathematical center for many years. Many participants of this conference were happy to visit this center, and it was a source of many mathematical ideas. And some of these ideas certainly will be represented in the lecture of Roman in this cycle of lectures. We are in long collaboration with Roman, with his students, and I hope this collaboration will be continued in the future, and this cycle of lecture is in some sense certificate of our common interest to the graph theory, to the group theory, and it's my real pleasure to hear a cycle of lecture which is suggested by Roman Nedela. So welcome, Roman, to this conference.
Okay, thank you very much for the introduction. It is a unique opportunity for me, and I'm really glad to have so many participants, more than 40, and there are even other people watching the talk from this place. Also, I would like to apologize that the talk, that my lecture will be more static than usual because I'm not at home and I've forgotten a presenter. But maybe it is not a problem because my first talk will be devoted mostly to introducing some concepts, and there will be basically no proofs. But later on, I will present also proofs online. Also, I would like, maybe I will interrupt it for a few minutes, I mean the presentation, and I will show something on whiteboard. I will draw some figures. Okay, so let's go on. First, something about literature, because there are students, not just experts. Of course, the basic literature is the book by Gross and Tucker, Topological Graph Theory, 1987, and there were some re-editions. But more, say, modern approach can be found in our booklet we produced with Sasha Mednik, supported by European grant. And here is the access. So you can find it there and loan down it, and it will cover basically the material of the first 3 talks. Okay, it is loaded and it will be available, so we don't need to spend time now here. So let me start with this. What is a graph covering? Also, I have to say that first I will be talk more informally about the main concepts. Later on, I will come with more precise definitions. So what is a covering? Covering is simply a graph epimorphism such that for each vertex, the epimorphism maps bijectively the set of darts based at each vertex. It is denoted by V bijectively. So we take an image of V, which is PV, and the star of darts, edges endowed with orientation, is mapped bijectively. So here it is, a dart is an edge endowed with one of the 2 possible orientations, but we think about this as implicitly. So it is not directly the same as a directed edge. Each standard edge, of course, or a loop gives rise to 2 darts, one way or the other way. The graphs considered will be locally finite. So time to time, we consider also infinite graphs, which are locally finite. That means degrees of vertices will always be finite. But multiple edges, loops, and even semi-edges are allowed. I will explain later what is a semi-edge. Also, we require that there are no isolated vertices. Simply in our model of graphs, there are no isolated vertices of degree 0. From the very beginning, I will explain roughly how coverings arises from group actions. There is a nice source of examples. If we have, okay, there is a nice distinction between algebraic and topological graph theorists and classical graph theorists. For classical graph theory, usually graph is denoted by G. But for algebraic graph theorists or topological graph theories, we use X for graph and G for a group. So we are doing basically topological and algebraic graph theory. Okay, so if we have a graph and a semi-regular group of automorphisms acting on X, we can easily construct the covering from X to the quotient X by G, which we denote Y. And how it is constructed, simply vertices are identified with orbits of the action of G, the same for edges. So these are the orbits, and an edge, which is an orbit, is incident to a vertex orbit. Yes, it's unstable, sorry. So an edge is incident to a vertex even only if the corresponding vertex orbit contains a vertex U, which is incident to E. It is not difficult to check that this really works, but one has to investigate what semi-regularity does mean in this particular case. Usually in group theory, a semi-regular action is defined that it is an action such that the point stabilizers are trivial. Sometimes it is also called free action of a group. But what means free semi-regular action in our setting? Well, by Gross and Tucker, this means that we take a subgroup of the automorphism group and the stabilizer of darts, vertices, and edges are trivial. So if we take this definition, then we have perfect understanding of what is a quotient and so on. But later on, there were some deep reasons for generalization. So there is a paper one fundamental paper by Malnic, myself, and Martin Škoviera, where we skipped the condition for semi-regularity of edges. So there may be, so automorphisms fixing an edge, and for instance, inverting, swapping the end vertices are allowed. So this is another definition. But the problem with this definition is that as a quotient, we are not getting a standard graph. And that new kind of edges appear. Simply an edge may be broken onto two halves, and we are getting a semi-edge. So it is incident just to one vertex, and it ends in a singularity. So this is one generalization. And later on with Sasha Mednik, we even skipped the condition to be semi-regular on vertices. But then we are getting not graph covering, but branched graph coverings. So this is first idea, or now I'm going to explain ideas which came, and later on I will formalize everything. A prominent example related to so-called regular coverings between graphs is a construction of Caligraphs. And actually many ideas which appeared later, which crystallized later when the theory of coverings was established, come from examination of what's going on in a Caligraph. So let me recall the definition. Given group G, we take a set of generators such that it is closed under taking inverses, and one is not in the set. And we construct a Caligraph KGS, whose vertex set is just elements of G. So vertices are elements of G, and two guys are adjacent if their X is the generator in X, such that H is Gx. So we define the incident by right multiplication in a group. And because the generating set is closed under taking of inverses, the graph is undirected, so it is symmetric. And also we can say that the edge GH in this situation is colored by where we identify X and X minus 1 by this couple. So we can think about equivalence relation, identifying element with its inverse, and we can think about this as a color, and we can attach to each edge the respective color. Suppose that S doesn't contain involutions, that means elements of order 2. We can form a one vertex graph with size S divided by 2 loops for each pair X to X inverse. And then it is easy to understand that if we can construct a covering from the Caligraph, taking X-colored edges onto X-colored loop. And this is a graph covering. This is really not difficult to understand, because what sort of subgraph is found in the Caligraph by X-colored edges? Well, it is a two-factor, homogeneous two-factor. Each cycle has the same length, and the length of each cycle in the two-factor is actually equal to the order of X. And this two-factor is mapped to a loop. So that means locally bijective thing, right? And we do it for every color, so it must be a graph covering. Here we have a first problem. We do like that involutions are not excluded. And the solution is that we extend the definition of our graph in the way that we allow the semi-edges. A special case of Caligraphs are circulants. These are the Caligraphs coming from cyclic groups. So let us take any subset of Zn not containing element 0, and let it is closed under taking inverses. Here it is expressed by S equal minus S because we are in additive group. And then this graph is known as a circulant. Usually we are restricted to connected graph, and this is reflected by condition that the greatest common divisor of the elements in S is 1. This is standard condition for generation of the cyclic group. It looks a very simple class of graphs, but few notes. Only recently, a complex polynomial algorithm was derived for recognition of circulants and for the isomorphism problem. The point is that if I give you the Kelly structure on a graph, then you see that it is a circulant. But if I give you some, I don't know, R-regular graph to decide whether it is a circulant or not, you need to find the group. Okay, group is easy, not so easy actually. If it is power of 2, you have a plenty of groups. So this is first problem. And second problem, there may be many choices of the generating set. Which one is defined? And also I have to mention that this was a surprise for me some years ago when I was working with circulants. Many standard parameters, including the independence number and chromatic number, are hard to determine. More precisely, the respective problems are NP-complete. So the class of circulants, which are the most simple Caligraphs, is certainly not an easy class to understand. Okay, why I'm talking so much about circulants and Caligraphs? As I mentioned, many ideas, which I will develop later, were just observed from this simple situation, from the covering or defined or from a Caligraph onto a one-vertex graph. Also, I have to mention from the very beginning that we can later discuss a generalization, that means branched covering between graphs. And there is an intimate analogy between many useful concepts and theorems in complex analysis and theory of Riemann surfaces and graph theory. It is sometimes really surprising how perfectly this dictionary works, and it is not known in general. So I'd like to share these nice ideas that there is some dictionary and you can translate statement from theory of Riemann surfaces to graph theory and vice versa, because this can lead to discovery of new proofs of classical results, or even to new discoveries at all. Graph theory, bit of philosophy. There is a general question in mathematics, not just discrete mathematics, how to describe large, finite or infinite objects and how to control properties of such objects. There are basically there are three essentially different approaches. Either we use induction or recursion, or we use probabilistic method, that means counting. The disadvantage of this method is that it is non-constructive. So we only get an answer that some object with certain properties exists, but it may not be easy to construct it. And the third approach is use of symmetries. And prominent example of the third approach is the construction of a Caligraph, and theory of regular graph coverings belongs to the third approach. And it is a very natural generalization of the Caligraph construction. Sample of application. Theory of graph coverings was born from from the attempt to solve two big problems in mathematics. One was the coloring problem. Everybody knows what is a 4-color problem. So that 4 colors are enough to color properly plane graph. But you may pose the same question for graphs embedded in surfaces of higher genera, like in Torus, for instance. You may ask, what is the chromatic number of graphs? What can you say about chromatic number of graphs embedded into Torus? It turns out that it is 7, and the maximum is achieved by a triangular embedding of K7 in the Torus. And you can ask general question, given surface, determine the chromatic number. So this is Heawood map coloring problem, and it took like 80 years. I think Heawood formulated it in the end of 19th century, something like 1890, and the proof was obtained by Ringel, Youngs, and some other collaborators which solved singular cases in year 1968, something like that. So it was really a deep problem, but how it is related to graph coverings? Well, the method, okay, so to determine the chromatic number, it requires to prove two inequalities. You have to prove that say certain function depending on the genus forms an upper bound, and then you have to prove that constructively, by constructing some examples, that it is achieved. Actually, it was not so difficult. In the Gross-Tucker books, you can find the proof on 2 pages length that this Heawood function is basically what it is, square subquadratic function, that it forms an upper bound. And the difficult part of the problem was to construct the examples. Sooner or later, people recognized that the problem is equivalent to find triangular or near triangular embeddings of complete graphs into surfaces. And to construct such guys, because N may have millions of vertices, one needs some idea how to do it. And theory of coverings was perfectly designed for this. So this was one of the resources from which everything developed. Simply, the idea was that from a one-vertex graph, from a one-vertex triangulation of some surface, one is able to construct the triangular or near triangular embedding of a complete graph Kn for n arbitrarily large. And that was, I mean, the book has something like 150 pages, so it is readable, and the for arithmetic reasons split into cases modulo 12. So depends on the class of n modulo 12. And later on, everything was generalized by Gross, Tucker, White, Stahl, and this classic part of theory is basically can be found in the book by Gross and Tucker I mentioned. Another source where the ideas, where it was useful is the construction of highly symmetrical graphs. And representatives of these directions are, for instance, Biggs, Feng, and many other people. What is the idea? The idea is that, for instance, I want to construct cubic 5-arc transitive graph, infinite family. Okay, so I first find one, preferably the smallest example. There is one on 30 vertices, and then I can use theory of coverings to construct infinite families. And in this way, and I can do it in the way that the covering graph remains 5-arc transitive. So this is really tricky. Then we use with Martin Scoviera the coverings in the theory of Nauher-zero flows. I will come to this later. I will show you some applications. It appears in spectral theory, but of course, language is different. But roughly speaking, if a big graph covers a smaller graph, then you can recognize it from the adjacency matrix. You can reorganize the adjacency matrix of the huge graph in the way that it contains blocks. And actually these blocks, they are homogeneous, and they code the covering graph, the target graph. So this is how they appear there. The construction of a cover over a small graph is frequently used, for instance, in construction of cages and near cages. The point is that you want to have the least regular graph, k-valence, say. Okay, input is the girth and valency, and you are hunting for k-valent graph, the least k-valent graph of given girth. It is a difficult problem, actually. If the girth is large enough and valency is greater or equal than 3, for many or for most of the pairs GK, the answer is not known. There are some estimates. For instance, if the girth is 5 and valency is 3, then everybody knows that the respective cage is the Petersen graph. So for small values, it is known, but there are just finitely many and few cases where it is known. There is another problem where the theory of graph covers tend to be useful, and this is the so-called degree diameter problem. It is sort of dual problem to the previous one. So now the input is diameter, and you have prescribed diameter and valence. You say diameter 2, valency 7. You can ask, give me the largest graph. It is not difficult to prove that the order of such a graph is bounded by a function depending on the valency and diameter, and so-called Moore or Moore bound. And you can ask how close one can get to Moore bound. Again, the construction of covers over a given graph can sometimes produce good approximations, and so on and so on. I think I'll stop here because I just wanted to let you to trust me that the theory of graph covers can be useful, and later on I will discuss some of the problems I mentioned in details. If you look from, this is a big picture. If you look to the theory from a side, what are the main central ideas? There are basically two main ideas. So either you want to find a small graph X sharing some property P, and you want to construct using theory of graph coverings infinitely many guys such that the lifts will also satisfy property P, so that you are in the class. And especially properties which are defined locally, that means you can control them just looking small neighborhood around the vertex, are fine for this application. The other idea comes from algebraic topology, and this is the projection part. We want to find, there is a concept of the universal cover. For some properties, not for all, we can find one graph or a small set of graphs sometimes, but one is the best. This is wanted. Such, usually this graph is infinite, such that that you can characterize the property in the way that all the guys sharing the property are quotients of the universal cover. This is if you have this is really perfect. Here factorization may mean factorization by particular semi-regular groups of automorphisms. If the property is defined like to be a lift of a graph X, then it is known that such a universal cover always exists. Is this end of story? Certainly no. This is just philosophy. But let me continue by two simple examples. For instance, let the property P1 is that X is connected and two-valent. Then one can easily deduce what is the universal cover. It is simply infinite paths. And obviously, there is an infinite cyclic group acting on the guy, and it contains for every n a subgroup of index n, and you can factorize, and in this way you can get all the cycles. How about property P2? This is more complex. Suppose P2 means that X is connected and X is locally C6. What does it mean? That the subgraph induced on the neighbors of every vertex is a 6 cycle. That means graph is 6 valent. What is the universal cover in this case? After some thinking, one realizes that there is some geometry behind. Because if you have a 6 cycle induced at neighbors of every vertex, then there are triangles. And each edge is shared by exactly 2 triangles. So you may find the triangulation. This graph triangulates a surface, orientable or non-orientable. But what is a universal cover for 6-valent triangulations? Well, everybody knows it. It is one of the regular tessellations of the Euclidean plane by equilateral triangles. And every such guy can be constructed by factorization by a proper subgroup. And one can prove that abstractly this subgroup is a product of 2 cyclic groups. Problems and exercises. What is the difference between the universal cover over a graph and the universal cover characterizing a property of graphs? Well, I basically gave an answer. The first one is a special case of the second one. Now a research problem. Which properties of P of graphs can be characterized by means of universal covers? I don't know the answer. I have some good example, very nice examples, but I don't know the general answer. Maybe such a general answer even does not exist. Last question, can I get different answers as concerns the existence of the universal cover over X if I require in the definition of tilde X that tilde X covers each infinite cover over Y of X as well? This is also not an easy question. It is related with some old paper by Bulitko. It is about locally homogeneous graphs. The property you can study can be defined like, I want that the subgraph induced by neighbors of each vertex is everywhere the same. This graph is called locally homogeneous. And then you can ask whether there exists an infinite or finite locally homogeneous graph or not. And Bulitko proved that this question to answer is algorithmically unsolvable. So this is really difficult. Not NP complete, but there is no algorithm at all. But for some prescribed graphs at the neighborhood, it can be answered. And we discussed on the previous slide one special case when the prescribed graph on the neighborhood is C6. For instance, if the order of the cycle is less than 6, one can prove that the universal cover exists, but there are just finitely many guys. For instance, if I prescribe C5, I have only two graphs, I think. Yeah. Okay. So homework, find examples of properties of graphs, much more than I mentioned. The universal cover exists and is finite. So this is a good training.
Roman, small comment, please. Okay.
Again, some philosophy. Sorry.
Very small comments. If you have a neighborhood which is a hexagon, this more or less means that we have a metric of zero curvature. If we have a pentagon outside, we have a metric of positive curvature. This is spherical case. And in this case, of course, there are just finite number possibility. If we have 7 gons, probably there are also possibility to create infinite covering. Just philosophy, of course, this is not result.
Thank you, Sasha. Yes, there are many partial results in this direction. Actually, these problems about locally homogeneous graphs were popular some times ago, and it is related with the proof of the classification of finite simple groups, because sometimes there was a local information, and the construction of Caligraph, of course, is very natural in this. And for instance, I can give you one curious result. There are exactly 3 graphs such that are locally Petersen graphs. This is very interesting result. But what the deep thing behind this is that really you are hunting for simple groups such that the Caligraph satisfies some local properties, and you want to use some ideas from topology, either to prove that such graph exists or that such graph does not exist. But this is another story. Bit of philosophy again. There are basically 2 approaches to graphs in mathematics. Algebraic, which basically says that graph is a relation. For instance, if we are talking about undirected graphs, then graph is a symmetric relation. And the topological, which defines graph as a 1 CW complex. Both approaches are fine, and both approaches are fine to solve different problems. What is interesting is the following: that basic problem of the standard definition of graph based on vertices, because you first, for the algebraic approach, you first take a set of vertices, and then you have this universal relation V times V, as simply graph is any subrelation of this universal relation. This sort of definition is, I mean, most of graph theory use this sort of definition, but it is fine for studying invariance of graphs based on vertices, but not so good for investigation of invariance based on edges. For instance, if we are talking about flow theory, then the other definition is much more comfortable, but many people don't understand this. Okay, for our theory, the problem is that quotient of a graph in classical algebraic definition may not be a graph, or we can make it a graph. For instance, if we consider just K2 and we want to factorize K2 by the involution acting on K2, in classical approach, the quotient is just vertex without edges. But then you are losing information. You are not able to reconstruct it. So what is behind our formalization of a graph is the topological definition. So if you don't understand something, you can check it as one CV complex. What does it mean? Okay, so now I'm going to formalize. Okay, now I am going to formalize our definition of a graph. So instead of vertices, we start with darts. We have an abstract set of darts, no structure. But we are thinking about darts as edges endowed implicitly with orientation. So we have some universe of darts. And we define a graph as a triple, the set of darts, some equivalence relation on the set of darts, and a dart reversing involution. So dart reversing involution is just involutory permutation in the symmetric group of D. Okay, so this is our object, but where are the standard graphs? It's not very understandable definition. The interpretation is the following. To create edges, we apply L. So we are, because it is involutory, the orbits are of order at most 2, and these will be the edges. And to create vertices, we considered equivalence classes on D, and we interpret it as the set of darts going out from a vertex. So equivalence class is a vertex. And these guys, we think about them as the star going out from a vertex. So this is very algebraic definition. And then, you know, the standard definition of homomorphism and everything and quotients and so on applies. So here is
but what
the explanation.
About ages? There are no ages at all.
Okay, so here is some explanation. So vertices are these classes. There are edges are orbits. If needed, we can introduce the incident function, which is defined by containment. And the idea is, again, we associate to a dart the starting vertex, the beginning, the origin, where it is originated. And now we can define formally what are the semi-edges. The semi-edges are simply, they correspond to fixed points of L. So these are orbits where you have just one dart. Lx is x. What are the loops? Again, you can formally define it like that, that the dart origins at the vertex Ix, and it is the same vertex as for the inverse guy, Lx. And Lx is not x, so that means it is not a semi-edge, right? So we have loops, and we can also introduce parallel edges. So all the standard constructions used in graph theory, all kinds of graphs are included. Now we can define the category of graphs as usually. What is a homomorphism between graphs? Here I am using the 4 tuple. So I have explicit vertices. This is the only difference, and I replaced the equivalence relation by the incident function. But this is the guy which commutes with the Dart reversing involution and with the incident function. So this is very algebraic definition. Alternatively, if we define graphs through the equivalence relation and Dart reversing involution, this means that x comes from the same vertex, x origins at the same vertex as y, then also this must hold for images. That's all. And I think now it's good time to have 5 minutes break. Okay, so we ended with a formal definition of the graphs with semi-edges and of homomorphisms between graphs. And now we are ready to formalize the definition of a graph covering. Okay. So, but first, how graph homomorphisms come from groups of automorphisms. Suppose we have our graph with semi-edges, and then we can formalize the definition of the quotient graph by setting D prime is the set of orbits of G on darts, V prime is the set of orbits of the action on vertices, then the incidence function is defined very naturally, and also the Dart reversing involution is defined very naturally. And actually, it is even not needed that the action is semi-regular and it works, but in what follows, I will always assume that at least the action on darts is free. It is semi-regular. Stabilizers of darts are trivial. Okay, so one exercise for students prove that X divided by G is well defined, and that the projection where we associate to X the orbit on X is a graph homomorphism. And there is one concrete example. Find K4, where the vertex set is 1, 2, 3, 4 as usually, factorized by this rotation fixing vertex 1. Okay, so there are some exercises. Next talk, I can start by discussion of the exercises, and I can show you some solutions. If you want to work by yourself, you can send me the solutions to my email, and I can reply whether it is fine or not, or where is the problem. So let's make such an agreement. So each next lecture will start with discussion of the homeworks and exercises from the previous one. Jesus Christ, what happened? Jak mi to blbne. Nedá sa mi posúvať. Čo? Ale mi to nereaguje. Ja neviem prečo.
Well, actually, everything fine with
There is some problem, sorry.
Mm-hmm.
So where do you want to be?
Tam, kde som bol. Jak sa tam dostať? Tá myška úplne blbá. OK, už viem. Okay, thank you. Okay, so let us continue. Some remarks. How I get in my model of graphs, simple graphs. That means graphs without semi-edges and so on and so on. So first I have to get rid to semi-edges. This is easy to see. This is easy to do. We just require that L is fixed point free and so on and so on. So all the standard models of graphs appear there. Also important note that to determine a homomorphism or an automorphism, it is enough to say what are images of darts. All the others can be derived from this, how vertices, for instance, are mapped, how edges are mapped. Okay, I can skip this, but here, so now we are ready to formalize the definition of a graph covering for our purposes. So what it is an epimorphism between two graphs such that the restriction, okay, we don't need actually to require that it is an epimorphism. It is enough to say that it is a morphism which is locally bijection. There is an alternative point of view which is more common in algebraic topology. We just may require that the fiber over a dart X intersect each set of darts starting at a vertex in exactly one dart, and from which we derive the so-called unique dart lifting property. So it says the following: if we take a dart in the target graph, and if we look the fiber over that dart, and if we fix a vertex in the lift, then there is exactly one dart which is mapped on the prescribed dart. So why it is epimorphism? It comes from the fact that it is locally bijection, because when the target graph is connected, one can easily prove that the covering projection is surjective. And in most consideration, we are restricted to connected graphs. I will say you warning when we allow disconnected graphs. Why graphs based on dart? I basically explain that there is an asymmetry in graph theory, while for invariant based on vertices, the algebraic definition of a graph is appropriate. But for investigation of graph invariants based on edges, this definition is not a proper one. And the first approach, algebraic definition and study of graph homomorphisms, is pursued in the book by Hell and Mitchell. There are many results there. Now we can revise the standard definition of graph, how it works in our model. So as before, so how we define a Caligraph in this model? Darts will be the set of darts is identified with the product G times X. And of course, as before, the set of generators is closed on taking inverses, and the vertices will be, as usually, just elements of G. The incidence relation is just the projection to the first coordinate, and the dart reversing, the action of dart reversing involution is defined here. So what it does, it puts inverse here, and it swaps vertex G to, it sends vertex G to vertex GX. And it is not difficult to understand that if you apply it twice, you are again getting GX. What is a bouquet of at X? It is a one vertex graph such that the darts are the generators, the generating set, and the dart reversing involution just takes an element onto a generator onto its inverse. And the incidence function, since we have just one vertex, takes everything onto the one vertex. And then the projection arising the first coordinate is the covering. And now we solve the problem with involutions because we have semi-edges. We don't have only loops, but we have also semi-edges that correspond to involutory generators. And now we can say very nice theorem that X is a Caligraph if and only if X covers regularly a one vertex graph. I didn't define what does it mean regular covering, but it will come. But this is really a nice statement. In the classical setting, one has to exclude involution and involutions in the generating set and to bypass this problem somehow, which is not very nice. And I will say in advance that the difference between regular covers and Caligraph's construction is only that we forget about one vertex quotient. We just take more vertices, we allow more vertices, but otherwise the definition is completely the same, right? So regular graph covers are just perfect and natural generalization of Caligraph construction. Once we have a Caligraph, again, one good idea which will be generalized. One can recognize two actions of G. One is by left multiplication, the other one is by right multiplication. And if the Caligraph is defined by right multiplication, then the left multiplication defines an embedding of the group G in the automorphism group, and everybody knows that this action is regular on vertices, on edges, and on darts. Not on edges, sometimes not on edges, but on darts. This, if there are involutions, then we are getting non-trivial stabilizers. A good question, when the left and right actions coincide. For those who know something from group theory, the answer is very natural. Exercise. Okay, so I have to warn again you that this Caligraph construction attach with a graph an algebraic structure. This structure, there is no unique way to do it sometimes. Think about complete graphs, right? If n is a composite number, there are many groups you can take, and then you take all the non-identity elements, and you are always getting complete graph, the same complete graph. So there are many representations, and there is a simple exercise. You can consider a three-sided prism, that means a graph on 6 vertices with 2 triangles joined by a matching. And there are 2 representations of this graph as a Caligraph. One is based on these 6, the other one on these 3. Determine the 2 actions for the dihedral case. And now a crucial concept. This is really important. Kelly voltage graph or ordinary voltage graphs in terminology of Gross and Tucker. Suppose we have our graph, our target graph, the small graph, and suppose we want to somehow reconstruct. We have just the target graph, and we want to define a huge graph so that it will cover my preferred small graph. How to do it? There is a very nice way. We introduce a mapping from the set of darts of the small graph to a certain, usually preferably finite group G. Assignment, no conditions, this is just an assignment. The only condition is that opposite darts they should get opposite evaluation, inverse elements in the group. So this is the only condition which is posed on this. And then once we have this, so graph with edges attached to darts, we can define a so-called derived graph. How it is defined? We just mimic the construction of the Caligraph. So as for the Caligraph, we define dart set to be the Cartesian product, D times G. The vertex set, again, the Cartesian product. Here is the definition of the dart reversing involution. So on the first coordinate, we mimic what's going on the target graph. On the second coordinate, this is the multiplication of the element by the voltage associated to X. And same story with the incidence function. Sorry. By definition, the projection arising the second coordinate is a regular covering projection. And again, as for Caligraph, there is a copy. The group embeds into the automorphism group of the derived graph. Okay, so this is a definition, and this is very useful definition. We will show many instances where it can solve a problem of construction of infinitely many graphs with prescribed properties. In this way, solving some classical problems posed in graph theory. There are some examples. For instance, everybody knows the generalized Petersen graphs, and this can be defined over a two-vertex graph where we have three edges, one edge joining the two vertices, and there are two loops. The other interesting exercise, try to determine n-dimensional cubes as derived graphs based on elementary abelian two group of rank n. And the last exercise, I mean, my first set of transparencies ends here, but this is not a tragedy if you like to continue. What is the time? 1:10, so we have still time. So we will continue with the other set. This is really something where you can see how nice is the theory. So prove that the derived graph defined by the next figure has diameter 2. I will talk a little bit about this. I mentioned the degree diameter problem, right? Suppose the input for the degree diameter problem is that we are hunting for a maximal graph of diameter 2 and valency is 7. What is the Moore bound? It is easy to count it. Pick up a vertex. There are 7 vertices adjacent to it. So we have 1 plus 7. And we want to maximize the size. So suppose at the next level, from each of the 7 neighbors, we can get to 6 vertices and nothing is glued together. So let us count. On the second level, we have 6 times 7, this is 42. At the first level, we have plus 7, and there was a first vertex plus 1, so this is 50. So the Moore bound, so the graph of diameter 2 and valency 7 cannot have more than 50 vertices. And your homework is to prove that if we take as the small graph, this 2-vertex graph, there are 5 parallel edges and 2 loops, and the voltage assignment from the group Z5 plus times Z5, that the guy achieves the Moore bound. that it achieves, it's easy because the group has 25 elements. So there is one orbit over one vertex, 25 vertices over 1, 25 over 2. So what is needed to prove is that it has diameter 2, because of course it is 7 valent because we have covering, we are constructing covering. So the derived graph is 7 valent graph on 50 vertices. What is needed to prove this is that it has diameter 2. And fortunately, this can be controlled algebraically from the bottom graph. You can think about the vertices in a fiber. So let's say the left one is U, that the vertices are indexed by the elements of the group. The same for the other vertex. So how the path of length 2 may look like. For instance, we can use this loop which lifts to some matching on the fiber. So we can first keep the fiber and then jump to the other side. So this is one possibility. Or we can first jump to the other side and then to move inside the orbits. Is there any other possibility? Yes, it is. We can go, say, first from left to right and then to move back. And if you investigate all these possibilities and you use that walking in the derived graph is reflected by multiplication, or in this case, addition in the respective group, you get the result. So this is fantastic example. I think it should go to basic monographs because I really don't know more simple explanation, more simple coding of the Hofmann-Singleton graph. And it is a unique graph because using some investigation of eigenvalues of possible candidates, one can prove that the Moore bound in this particular case for diameter 2 can be achieved just in 4 cases. For 3 cases, we have construction. Case k equal to 2, this is just pentagon. Case equal to 3, this is our well-known Peterson graph. For 7, it is the Hofmann-Singleton, and there is one more value. I don't remember it. 57, yeah. There is 57 where it can exist, but so far nobody was able to construct it. So it might be that there exists a huge graph. You can count the same way as we derive 50, but it contains thousands of vertices if it exists. And our nowadays computers are not fast enough to check it use the existence. So it is still open question for decades. Maybe you can have a luck and you find some construction, but I have to warn you that it is now known that the group of symmetries is small if it is not rigid. This means such a nice trick, like for the Hofmann-Singleton, where you have 2 orbits acting on the graph of size 25, will not work for the construction of the missing Moore guy. So this is what I can say. So what the time? So, okay, so since we have another 15 minutes, I try to open another set of slides. Okay, stop sharing. What I have to do is should open this one. Dôležité to poradie. Where it is? Is it share? Yeah. Can you see it?
We can see it.
Yes. now I have to Control L. It should be okay, right?
Yeah, it is full screen. Good.
Okay, so let us continue. So now a little bit more theory. I'm sorry for this, but before I show applications, we need to learn something. And this is also a very fundamental thing. If you had a course in algebraic topology, you will recognize where from the ideas come. Once we have a graph based on darts, it is, okay, so what is a walk? Walk is just a sequence of darts such that if you take xi plus 1, it originates in the same vertex where the previous dart terminates. So this is very standard idea of a walk. So compared to other concepts in graphs, the set of walks is infinite, right? Because, for instance, it's enough if you have one edge and you can go there and back, and you can do it how many times you want. So the set of walks is infinite by definition, except, but we don't consider graphs without edges. Okay. Also, it is clear what does it mean that the dart is closed. Here it is written in formal way, but it basically means that the terminal vertex of the walk is the same as the beginning, as the origin of the walk. But what is important is that these operators, the incident function and the dart reversing involution, naturally extend to the set of all walks. What we do? Okay, the incidence function is completely easy. What is the start origin of a walk? It is the origin of the first dart in the sequence. How about the dart reversing involution? So what we do is we instead of reading or traversing the walk from x0 to xn, we traverse it in the opposite way, but then of course instead of the original darts, since we are traversing them in an opposite way, we have inverse guys. Here I'm using convention that Lx is the same, I identify with x to minus 1. Okay, this is nice, but also good idea is that walks with the same terminal and initial vertex can be concatenated, right? So we may create a new walk from 2, provided the first one terminates in the same vertex where the other originates. And this is a partially defined product on the set of walks. And sometimes this structure is called fundamental groupoid. Fundamental groupoid becomes a group if we restrict ourselves just to closed walks based on the same vertex. Then it is a group. But we have to extend the definition. Okay, so we have to include the trivial walk, empty walk. So this is then the identity in the group. And inverse walk is just we apply this operator L, right? We traverse it from the other side and we exchange the darts to their inverses. Everything is fine. And the set of this, so what is an irreducible walk? Still, I need to say something. The idea again comes from algebraic topology. In topological space, we have an idea of contractible walk. So think about contractible loop on a surface. So we can contract it into a point. But in graph, this means, so what is an irreducible walk? This means that we forbid subsequences of the form x minus 1. Quite simple. So we don't need to introduce complex definition of what does it mean to be contractible. We just, for irreducible guys are the walks which doesn't contain a sub-walk of the form go there and go back immediately. And irreducible walks with the product operation of concatenation forms the fundamental group of the graph. Okay. So we have fundamental groupoid and we have also fundamental group of the graph. The question is how, okay, if the graph is connected, this is also standard idea from algebraic topology. The 1CV complexes are very nice spaces. And if it is connected, all the fundamental groups are conjugate. So it doesn't matter where we pick up the vertex. So they are the same from the point of view of group theory. But what is the structure of the fundamental group of X based at the vertex V? Also not so difficult to understand. There is a standard approach how to get it. Choose a spanning tree. Spanning tree is, everybody understands that spanning tree is contractible to a vertex, right? And then what remained are cotree darts. Each cotree dart in a spanning tree defines a U-based loop. It may not be a simple loop because you have a unique path going from the base vertex to an origin of the dart. Then you use the cotree dart and then you go back. But these two paths may have non-empty intersection. So it may not be, I mean, what happens may not be what these basic, these fundamental cycles are not cycles sometimes. They are just closed walks, but doesn't matter. But what is it? So, and using this idea, actually, there are no obstructions, there are no requirements. So what does it mean? This means that the group is just free. And what is the rank of the group? It is the same as the rank. Okay, if there are no semi-edges, we can compute it easily. Take the number of edges minus number of vertices plus 1, so-called Betti number or cycle rank of the graph. However, now we have also semi-edges and we have to reflect it. And something happened with the fundamental group because at the end of a semi-edge, there is a singularity of index 2. So what happens is the following, that if there exist semi-edges in our graph, the fundamental group is no more free group. It is a product of infinite cyclic groups and times the free product of Z2s. And each Z2 corresponds to one semi-edge. And it is not, I mean, we don't have freedom here. I mean, okay, we have a freedom, we can define it in another way, but then the theory will not work. So this is the only way how to define, this is forced simply. If we want the theory to work, we have to slightly change the definition or extend, better to say, the definition of the fundamental group to graphs with semi-edges. I hope everybody understands what is a free product, but if you don't have education in group theory, just imagine that what is a free product of two guys, for instance, Z star Z. You take all the words say X is Z is generated by X, and the other copy of Z is generated by Y. So you take all the words in terms of X and Y. Exponents are allowed, integer exponents are allowed, and this guy together with concatenation, this is the group. This is one of the models you can get. Okay, so the definition of the fundamental group was changed, and the reason is that we replaced standard graphs by the very modern word, or not so modern but not so old, is that we are now replaced graphs with orbifolds. So actually, these semi-edges, this existence of semi-edges means that we are working with dealing with one-dimensional orbifolds with singularities at three ends of semi-edges. This is topological point of view, if you like, or geometric point of view. So nothing happened because all the classical graphs are included, only that we have extended our definition. And there were some deep reasons why we did it. Part of the reasons I explained. The algebraic reason was that we wanted to have theory closed undertaking quotients. And because of that, standard graphs were simply not sufficient. And it is not a good theory if it is not. I mean, what sort of algebra it is if you are missing quotients? I mean, this is stupid. I mean, from the pure algebraic point of view, this is not good, simply. So everything is very natural. And since my time is over, I will just finish with some little story. With Martin Škovjera, we introduced these graphs with semi-edges in 90s because we got this feeling that something is missing. And we were so proud that everything is now ordered and so on, and we are getting nice results and nice statements. But after some years, we realized that theoretical physicists, they discovered it 20 years before, and they call semi-edges lex. So this is a nice story that one shouldn't be too proud in mathematics, because the old mathematicians discovered almost everything.
Right.
So they have a little room to find some really fundamental new concepts. But anyway, it is at least what is fine is that we were at least as clever than our predecessors. Thank you very much.
Thank you very much, Roman, for your great talk. Are there any questions to the lecture?
Yeah, I hope I will be listening them. Let me move to reproductor.
Yeah, sure, please.
If it's possible, I have a few questions.
Oh, yeah, sure, Alexander, please.
Roman, do you hear me? Okay.
I hear you.
So the first question is the following. Suppose we have a graph with some prescribed property. For example, each neighborhood has a hexagon structure. Our aim is to create universal covering with this property. Did you try to construct a fundamental group which reflects this property in such a way that covering admits an action of such a fundamental group and a result of factorization of universal covering by action of this group give us a original graph? You understand my question?
Yes, I understand.
So what is known in this direction?
There is some general trick how to do it.
Yeah.
You have to replace I know the answer in this particular case, but I don't know the general answer. In this particular case, if we are talking about locally cyclic graphs, locally Cn for given n, it is easy to understand that each such a finite graph defines a certain regular triangulation of a compact closed surface, orientable or non-orientable. So this is first observation. So what we did actually, in the beginning we have just graph, but we recognized that every triangle of the graph can be made solid. So you put a two-cell there. In this way, you form the surface, and then you understand what to do. In general, in this theory of locally homogeneous graphs, there are some tricks used you can do it in general, because if you say that something is locally whatever, then every edge between the two neighbors define a triangle. So you replace one-dimensional complex by two-dimensional complex by adding cells to each triangle of a graph. And then some interesting things happen. For instance, the existence of infinite cover may depend on the structure of the second fundamental group. If it is trivial, and if you have one finite example, there exists also infinite one. If it is non-trivial, then it may happen that the universal cover infinite guy does not exist. So something is known, but not everything.
This is just local structure of neighborhood, but you put more general problem, as I understand, yeah. So not exactly these properties, maybe some more general properties. But in any case, it's very interesting to construct a kind of fundamental group which is responsible for covering. Maybe we don't need to use Riemann surfaces in this case. To use just very abstract construction, like construction you show us in the last part of your lecture. So we have to introduce some equivalence between these closed walks. What kind of closed walk are equivalent in this situation? Equivalence related to property P, but I don't know how.
Sasha, I understand your point. Basically, this is about what does it mean contractible?
Yeah, correct.
For each case, you have to investigate what is contractibility, and then you are getting the correct definition of the fundamental group.
Sure, yes, correct. No, I should say that I enjoy a Roman lecture. Of course, I know this subject by philosophy was very interesting, sometimes very unexpected for me. So in general, I learned a lot for me personally. And I hope that in the next lecture, I will be happy to learn more and more. So thank you very much, Roman.
Thank you also, and I'm glad that I have lost only 5 listeners during the 1.5 hour.
Yes, that is true. Good result.
Out of 40.
Right. Are there any other questions?
Thank you, Roman. Thank you.
Okay. Well, okay, there is no questions, and let us thank our speaker again. Thank you. It was really wonderful lecture, and I hope to see you in 2 weeks. In 2 weeks, the lecture will be conducted by Sasha Medner. Okay?
Okay, bye-bye.
Roman, are you with us?
Bye-bye.
Okay, see you in 2 weeks. Bye. Thank you very much.
Bye-bye, bye-bye.
Bye. Yeah, it was great. Yeah, okay.